So hey everybody, thank you so much for coming today. I really appreciate it. It's a real pleasure. Actually, my son, Alan, would probably extra get a kick out of this thing. He actually took a couple of pictures. He's our astrophotographer in our family. But also he's a wireless radio guy. So W1AF is the station where he uses it. So I think you'd have a lot of fun coming here today. But thank you for having me. Today, our conversation is about the end of star formation. My goal is to talk for 30 minutes, so I'm going to be watching the clock. But all of you are welcome to set your clocks for 30 minutes, and if everything starts chiming at 30 minutes, then I'll know that I have gone too long. The plan is to sort of stop at 25 and then take as many questions as you all have. So, I think the story of this talk is about, well, when I first started thinking about this topic, what happens when star formation ends in a galaxy, it was not particularly fashionable. In fact, the galaxies about which I'm about to tell you were considered mere curiosities back in the 1980s when they were first identified. But they actually have some real significance today because, as with all things in science, something that seems uninteresting or unusual once becomes mainstream and important sometime down the future. Right? I remember when I first started in astronomy as a graduate student, the hot topic was the cosmic microwave background, right? This cosmology. Everyone wanted to be a cosmologist. Nobody wanted to study planets because no one had ever found a planet outside our solar system, right? But now, a couple decades later, exoplanets are the hottest thing in the field. Every new, sharp young person wants to do exoplanet. Cosmology is still cool, but we've already pretty much figured out a whole bunch of things about the universe in the past couple of decades. And so things just keep cycling. So maybe the lesson of this overall conversation that we're going to have today is if you like something in astronomy or in life, just keep doing it because it's cool. Sooner or later it'll become fashionable. Don't worry about chasing the sexy thing at any given time. Certainly that's what happened with me. So this is a telescope which some of you may recognize. This is at Magellan, one of the Magellan telescopes down in Las Campanas. And as you can see clearly, this is taken not from that telescope, from sort of over here. That's the Milky Way. You see the Magellanic Clouds over on the side, and then the coal sack in the middle. Right. I'm going to zoom in to this area so you can get a sense of what we're talking about. If you see the coal sack, most of you know that this is just a gas cloud that's quite cold, and it's quite dusty. So we can't really see what's inside. But inside, stars are forming. Right now, the coal sack is a little bit unusual. It seems to be forming fewer stars than you might expect for a molecular cloud of its size, but we're not really sure why. But stars are forming inside there. And what happens, of course, is if a very bright star forms in a gas cloud, eventually all of its radiation starts to blast through the cloud, just like clearing fog in the morning of a foggy morning or something like that here on Earth. And eventually you wind up creating these kinds of nebulae, right? The red spots that you see. A hot, massive star, Eta Carina, of course, an exception, one of the very brightest stars that we know of. But what happens is that the ionizing radiation winds up ionizing the hydrogen that's in the region around the star-forming region, the star itself, and thus gives off that characteristic red H-alpha color. Right? So, for the first part of my graduate career, I was looking at starbursts and H2 regions and trying to understand how stars form and what they did and so on. But then something fun happened. If you see the galaxy, the Milky Way, as you know, it kind of probably looks like this from the outside along the edge. And then if we look at it on the face front, you see all these little dots. Right? This is maybe more star forming than our Milky Way would be. But as you can imagine, if we were looking down at our galaxy, it's a little off too because we have a bar in our Milky Way. You guys all know we have a bar in the Milky Way, right? It's small, but it's kind of there. But it kind of looks like that. And I was counting H2 regions. We had an H-alpha filter, and my advisor at that time had taken a picture of big face-on galaxies with an H-alpha filter, and then with a filter about the same width, but not on the H-alpha line, so further over. So the idea was to subtract one from the other and then bless you. Then count the different H2 regions and get a sense of what the star-forming rates were and what the characteristics of those rates were. Was there a dust differential from the center to the outside? Is there an age differential? Those kinds of things. So it was kind of fun to do. Other galaxies, not forming stars so much, but this is the Sombrero, as most of you know. Does it still look like a sombrero once the HST is mounted through it? I guess it kind of does, right? Yeah. Or two of them anyway, right? Sombrero's floating on a pond. It's kind of what that looks like. And you can see the strong dust lanes right down the center of the disk here, and then the very large bulge in the middle. Now, lenticular galaxies are somewhere between elliptical and spiral, as you all know. Elliptical galaxy looking like this. This is one of the big ones inside one of the big clusters of galaxies, and it has lots of little galaxies and globular clusters and stuff like that surrounding it because it has been consuming other galaxies for a very long time. Right? Now, this kind of galaxy, these ellipticals, they're not forming stars anymore at all. Right? The lenticular galaxies, they may be forming stars a little bit, and the spiral galaxies, like the one we live in, they're forming stars a lot. So what makes things change from star forming to not star forming? And my advisor at that time thought that merging galaxies would cause that thing. It was a hypothesis. By the 1990s, it was pretty well confirmed that if you take two galaxies that are rich in gas and you smash them together, over the course of the billion years or so it would take for them to coalesce, you would wind up with huge amounts of new star formation. Okay, so this is a famous whirlpool galaxy, and the thing next to it, NGC 5195, right? And they are colliding. This is a fascinating pair, by the way, because both this one and that one have active nuclei. So they have supermassive black holes in the center that are accreting material. It's a neat system to look at, and we've seen things that look like this, but many billions of light years away, which are fascinating objects of study in terms of the evolution of galaxies. But as they collide, you get something like this. This is NGC 4676 A and B, known as the mice. And they actually do kind of look like mice, I guess. Although in these nice Hubble photos, they look more like galaxies. And they have these strong streamers coming out from there. This is not actually straight, but it's curved in such a way that it looks to us as if it's straight. It's kind of curled this way. These are two spiral galaxies that have crashed into each other. This collision is believed to be about 200 million or so years old. So it's in the process of the collision. And this has already probably passed through once, and is coming back in again for the second collapse as they come in together. And that's just from all the dynamics of measuring the motions of the star. But these tails, notice that the tidal tails are quite blue. Right? And then you have these other stars in the middle here. So there's a lot of star formation going on here. Young stars, bright stars, all caused by this interaction, disturbing the gas and creating bursts of star formation. And then here's a classic frame. Many of you can find this. My friend Aaron Evans down at the University of Virginia. Actually, I'm going down there to give a talk next Friday, or excuse me, next Thursday. Sorry, Aaron. Sorry, I'm talking to the camera too. It's probably a bad idea. It's just my TV habit. Anyway, using the Hubble Space Telescope, this is just a card, what do they call these things? A menagerie, shall we say, of many different ways that galaxies collide, how long it takes for them to collide, and so on. This one almost looks like what? Something going through a Stargate, right? Yeah. So it's fascinating to look at all these things and see all the different things that can happen with galaxies colliding. And keep in mind, of course, that although these galaxies are coming toward each other at hundreds of thousands or even millions of miles per hour, they are so large that a single pass takes more than 100 million years. So it's really dynamic activity, but to us they seem like they're frozen in time. So this is...
Is there a distance, the common distance of those? Are they a billion light years away? I mean, is all this activity happening in a space of time?
It happens all throughout the history of the cosmos. In fact, the merger rate of galaxies has changed since galaxies were first formed. It's a very important part of research, actually, to know what the rate of galaxy collisions were 12 billion years ago, 11 billion, 10 billion, 9 billion, 8 billion, etc. because we need to know how the galaxy population has been changing over time? That is a very good question. So, my studies of starbursting galaxies and merging galaxies led me in 1990-something, 1, 2, 3, something like that, when I was still a student, come across this galaxy. Right? This picture was taken much later, but this galaxy, if you can see here, it looks kind of like a spiral galaxy maybe, but it's got this sort of tail coming back this way. A little bit of a tail curled this way, so it's kind of like a backwards comma or an apostrophe or something like that. And this galaxy was really cool because it was a galaxy that marks what might be the product a billion years after two galaxies collide. The gas by that point is probably used up or blown out of the galaxy. You're not forming new stars anymore. What's left? So when the star formation is ended, this object shows up. All right, something like this. And I was very excited to study this thing, but like I said, it was just one object. Right? But anyway, I'll tell you why it becomes important later on. This object was just called G515 because when it was discovered, it was the 515th object in a big galaxy survey that people were doing. And this one looked just like a weird, pesky object, and it turned out to be interesting enough that the authors, Overly, Hill, and Hessel, wrote a paper about it. And I read it and I said, this is cool. You know, I gotta study these things more. All right. So later on, the reason I have the other name Magellan in front is because when more than 10 years later, I was at the Kitt Peak 4-meter telescope, the Macaulay telescope. We were taking infrared images of this object. And my friend Dave Thompson, he looked at this thing for the first time. He hadn't seen it before and said, we have to give it a name. I said, okay, other than G515. It's like, yeah, that's a boring name. And he said, well, you know, this reminds me of biology class. And you know the euglenas that you all may have remembered from high school biology class? They were little microorganisms with a whip-like tail that got them around, right? And the little tail is called a flagellum. So this group of microorganisms with flagella were called flagellates, right? You know the scene in Monty Python, you know, yeah, those flagellates. So he said, we're going to call this flagellum. Yeah. It's like, okay, so now it's called flagellum. That's not an official IAU designation, so don't worry about that. You can call it whatever you want. So why is this so cool? Well, it really comes out in the spectrum. We already know it has this weird shape, right? Which is very well likely the result of this collision, and a billion years later, there's a little tail still left, but most of the galaxy is coalesced into a single one. Now, when we look at the spectra of spiral galaxies, they look like this. How many of you have done spectroscopy before in either astronomy or anything like that? Okay, so it's appropriate for me then to tell you all that when we look at spectra, the hydrogen alpha line, the H alpha, which makes such beautiful red the photographs on our telescopes, is this one. Okay, this is redshifted, so it normally lives at 6,563 nanometers right here, but it has been redshifted because this object, this particular galaxy, is far away. But nevertheless, notice that it says a sharp emission line here, and then there are these other sharp emission lines, H beta and oxygen 2. Those are indicators that star formation is happening vigorously. And we see that's true. We see all the H2 regions in the picture. Right? This is what it would look like. Now, pay attention to these lines here. That's an interesting part. These are absorption lines of hydrogen. Okay? Those are produced by A stars. And remember the O, B, A, F, G, K, M of stars? A stars and B stars, they have very strong absorption in the hydrogen line, H delta, H gamma, things like that. They are not the oldest stars. They are stars that are about 1 billion years old, or a little bit less. So if you have a lot of those stars, then you see these here. Right? In this case, we see that this galaxy has a bunch of those A stars, but it also has a lot of ongoing star formation, as indicated by those sharp lines. Now, we go to an elliptical galaxy, and you see it's a very different spectrum. Now you see that there is no H alpha emission, right? It's all gone. That's because there's no star formation. That emission that you would normally see from the ionized gas surrounding hot stars is gone. And you don't see the absorption lines of H beta, gamma, and delta strongly either. Instead, you see this very sharp break here, right around 4,000 angstroms. That's because the calcium, K, and H lines, which are very strong in G stars, like our sun, have taken over the optical portion of the spectrum. So if you see a very sharp drop here, and you have this deep absorption from the calcium H and K lines, then you know that star formation is not dominant, but rather older stars, billions of years old, instead of a billion years old, are the primary contributors to the optical spectrum. Okay. So here's our flagellum again, taken in different pictures, and it's called E plus A. All right, you see this. Why is it called E plus A? Because if you look at its spectrum, it seems to be right in the middle between the two. Right? An elliptical galaxy, sharp jump, no emission lines. But these Balmer absorption lines are very strong. So this galaxy is a combination, right? Elliptical galaxy spectrum, old stars not forming any new ones, but a whole bunch of 1 billion year old stars sitting within this otherwise old population. How do we interpret this? It's that this galaxy had a big burst of star formation about 1 billion years ago. The billion-year-old stars are still around. The young stars, the million-ish-year-old stars, the ones that shine brightly in the ultraviolet, the ones that help produce the emission lines, those are all gone now. They've blown up in supernova explosions. So you've got the E plus the A. This is what happens when star formation ends in a galaxy. Pretty cool, right? So I think it's cool anyway, but it's kind of boring. If you look a little further, it is, right? You see this big, huge H images. So people are like, okay, they're kind of cool, but they're kind of boring, aren't they? And I said, yes, they are, but I think they're cool because after things die, that transition is interesting to me. Again, I wrote a few papers about this in the 90s, but again, people are like, oh, okay, that's nice, but so what, right? Because it wasn't hot or anything like that. I looked at it still further, and I followed it up about 10 years ago, and I've been watching this thing ever since. So it's been about 25 years I've been following one object. Now, 25 years is a long time for us, but for a galaxy, it's kind of a drop in the bucket. But there is a way in which galaxies can change on those short time scales. Okay? And so I didn't even think that it would happen, but it did. How do they change on such short time scales? If they have a supermassive black hole in the center that happens to be swallowing, or where things are falling into, dust, gas, maybe blobs of stars, then depending on the rate of flow into the black hole, sometimes the galaxy can flare up or die down in certain emission lines or in radio emission. Okay? So the variability of the central supermassive black hole system may give you a clue that things are going on still. So looking at the center, you can see that if I'm trying, can you see this? This is kind of small. But you can see that I looked right at the center of this galaxy. Imagine looking right through there and measured spectra. This particular spectrum was taken with a 90-inch telescope, so 8.5 feet across, about 25 feet high. It's on Kitt Peak. It's a beautiful little telescope. It's kind of fun. But by looking with that, I looked right at the center of it, and you can see that there are emission lines, but these emission lines are not hydrogen, right? The one that should be hydrogen is here in the middle. It's this little tiny divot, if it's there at all. I mean, I could imagine that that's just a noise block, right? But in a star-forming galaxy, it would be way up here. In a regular non-star-forming galaxy, there'd be nothing here. Yeah. But these two lines on the side, they are produced by low ionization gas. Right? Gas that could be caused by strong interstellar winds blowing out of a supermassive black hole system, okay? Or the kinds of shocks that you can produce when you have accretion onto a supermassive black hole, and then the result is this energy of the stuff that didn't fall all the way down, but it's kind of sped up and otherwise energized in the falling process. So I looked at that and I thought, well, there's stuff going on in the middle. I'm excited, right? This supermassive black hole system is not totally dead. It is, again, a Monty Python reference, not dead yet, right?
Before you move on, what are
Yes.
the 6 different panels?
Oh, yes.
You pointed at the core.
Right. The 6 different, all these panels are how far away I am from the core. So this is at the core. That's just under 1 arc second away from the core, in that direction. Right. This is 1.7 arc seconds in that direction, 2.6, 3.4, and then in the other direction. So along this aperture, the spectrograph slit. So it's just showing that in the center there's a little something, but as you get further and further away from the center, there's nothing.
Is this still optical or is this right?
This is still optical. It's right in the region of H alpha and nitrogen 2. Okay. Good question. So, looking further, another way you can tell that something is going on in a galaxy, even though you can't see it in its optical spectrum, is looking other wavelengths. Right? What happens in the radio? What happens in the infrared? Have any of you remember the infrared astronomical satellite, otherwise known as IRAS? Yeah. Great, wonderful little mission that ran in the 1980s. What it basically did was, although it had very low spatial resolution, it mapped the entire sky in wavelengths ranging from 12 to 100 microns. Okay. Remember, the human body emits infrared radiation at about 10 to 12 microns. Right? So this is colder than the human body. So normally this stuff gets to this high temperatures not from stars, but from dust. Interstellar dust that gets heated up by some internal source, and then the dust glows. So without being too technical, but being a little technical, because I know you all can handle it, this is the 12 micron, 25 micron, 60 micron, and 100 micron wavelengths of the images or the scans taken using the IRAS instruments. And you can see that there is no bump at 12 and 25, but there's a significant bump at 60 and another significant bump at 100. This blob right here, that's a nearby galaxy far away. It has a very strong IRAS signature, but we're looking at this one. Okay. So again, this galaxy does have mid-infrared emission. If there are no hot stars, what's heating the dust? Probably a supermassive black hole at the center. Like a quasar, but faint, somehow able to be suppressed. Right? So, finally, best way to look for whether or not you have a supermassive black hole in the center of a galaxy is whether or not the radio continuum works. This is variability. Remember I told you that over time scales of a few months or a few years, the radio emission can change if you have a supermassive black hole going on? And this is what happened. This is archival data from something called NBSS, taken in 1995. This was taken by what's a survey called FIRST in 2000. It's there, it's not there. Right? There, not there, there, not there. Woo! I know, it's like, again, excites me, didn't excite a lot of other people. What does that mean to me? What did that mean to me? It meant that this end of star formation caused a supermassive black hole to ignite. Probably in the past billion years, it had a lot of activity. A lot of stuff fell down into it. A quasar or some other kind of activity was going on, QSO. And then now it's sputtering. It's at its end phases. And it's kind of just chugging along a little bit. It's able to heat some dust. It's able to create radio variability. It's able to create some low ionization stuff. But it's kind of done. So when a galaxy's star formation ends in a collision, it also brings to an end its supermassive black hole activity. But the fact that one is there and things are going is neat. So I think it's cool. And then what happened? Well, about 10 years ago, maybe 5 years ago, people started doing studies not just of a few hundred galaxies or a few thousand galaxies, but hundreds of thousands of galaxies. I got involved with a project called Cosmos, which is the largest single contiguous area ever surveyed by the Hubble Space Telescope to look for galaxy evolution out to 10 to 12 billion light years from the Earth. And as they measured stuff, well, they realized, wow, galaxies, they were forming stars really vigorously in the past. And now, on average, vigorously star-forming galaxies are few and far between. So most galaxies in the universe have had their star formation end. The end of star formation is an important ingredient in the overall evolution of all the galaxies in the universe. So, about 5 or 10 years ago, this thing which I said, these E plus A's, this Magellan type galaxies, which were just merely interesting curiosities, suddenly became important in understanding how all galaxies change in the universe. So now this question, which we call quenching, star formation quenching, is a major astrophysical problem. So they're still rare. These E plus A galaxies are still hard to find, but now, instead of being mere curiosities, they're important signposts as we try to understand how the entire universe has aged since the Big Bang and the formation of galaxies. So I think it's kind of cool. So in the end, yes, boring, but cool. I don't know. Again, it's not exoplanets, but I think it's neat, and I've enjoyed working on this for many years. So what is next? Remember that I showed you that there was just one spectrograph slit that I used to take the images of that galaxy. Imagine taking fibers, optical fibers. This is technology that's only been available in recent years. Certainly wasn't available when I was a graduate student. Take it all together and pack them together in various configurations, either hexagons or rows, various kinds. And that way you can get many spectra across an entire face of a galaxy. You don't have to rely on just one axis. Right? Here's an example. If I took, actually, some friends of mine, Marshall Wolf and Eric Cooper at the University of Wisconsin, used something called Sparse Pack. It's an integral field unit, and another thing called X Pack, and took spectra of G515, or flagellum. And that analysis is still ongoing. The idea that maybe if we can find the stuff in the center that's really optically exciting, but then we go off to the side and it becomes less and less exciting, can we map the age of this galaxy, right? There's ages of the stars, and from the center all the way out. That will really help us understand how the aging of galaxies goes, right? At least in this one. Did it say stop forming stars on the outside before the inside? Did it stop forming stars all at once, all throughout? Or maybe there's a pack of star formation going on somewhere that we just haven't found yet. This is a very fun thing to do. You can see all these spectra, there's different spots on this galaxy, Magellan, and it's so much fun. I love this. Okay, all this is a prelude tonight. So my most recent research right now, it's ongoing now, is with Manga. And Manga is a fanciful name for a project that's related to the Sloan Digital Sky Survey. Right? What is that exactly? You've heard of the Sloan Digital Sky Survey in all likelihood. It's a beautiful system that has been running for almost 20 years now, where people automatedly, but not robotically, right? With automation, are able to use this one telescope in New Mexico to take uniformly high-quality data of hundreds of thousands of different objects over the course of many years, over and over again, and then make it all available to the general public. You can all go to sdss.org and start analyzing your own science anytime you want to. I strongly encourage it. In fact, there's a lot of data available to do neat things. So what happened with, obviously this is not last week, it's July 21st, 2014, so it's 4 years ago now, last week. But by taking these IFU bundles and putting them on 10,000 galaxies in the local universe out to a distance of approximately 1 billion light years. What we're doing is to get a sample of a whole bunch of different galaxies across the space. And what I have had my students do over the past 4 years is every time a new tranche of data comes out, they come out about 1,500 at a time. They look through the data to find E plus A galaxies, to find these galaxies whose star formation have ended, and to find out how quenching has gone on in those galaxies. And from there, we can find out how quenching happens in general, and maybe extend it to the entire universe. Okay. I will just point out Karen Masters right there. She's a good friend of mine. She's now at Haverford, and she's the spokesman to the Sloan Digital Sky Survey. I still talk with most of these other folks, but Karen is my main collaborator at Manga, and she is really, really good. She also, by the way, is the project scientist for Galaxy Zoo. So if any of you have ever done that citizen science, that's Karen. She's in charge. And she just gave a talk at the Astronomical Society of New York's 50th anniversary meeting last week, which happened at the American Museum of Natural History, about Sloan and Manga. It's just brilliant stuff that they're doing neat stuff. There's a lot of science for you all to do. You can all feel like participating. This is what the Manga fiber bundles look like. They're plugged into these aluminum plates and then slid in through cartridges in and out of this big telescope. It's a 2.5 meter telescope, excuse me. And then here are the spectra that can be provided. Right? Once again, you see this red one. That's an elliptical galaxy, and then this blue one is a spiral galaxy. And you can find all of these different lines, whether they're sharp and star-forming indicators, or whether they're non-star-forming, or the smaller lines, and whatever comes in between allows us to really study the histories of the star formation of the universe. Here's more information about the Manga IFUs, and then here's some examples of the data that we can get from them. All right. This is just a galaxy. It's a test galaxy. If you just look at its regular light I-band is approximately just beyond our eyes from the end of the red spectrum all the way close into the infrared. But you can see, you can map the velocities of things. This false color shows gas. That's redshifted gas. So the gas in the galaxy is moving away from over there, is moving toward us over here. You all know what that means, right? Galaxy is spinning. It's spinning this way. Right? That's cool. But wait, there's more. This is H-alpha flux, right? H-alpha, remember the star formation? From this, we can find out exactly where all the star formation is going on. And the most extreme star formation is in this clump over here, right? Not in the center, but off to the side. That's cool. Who knew that could happen? But wait, there's more. This is what we call metallicity, all right? In strange units, 12 plus log over H, R23s. Just a technical term for saying what fraction of the mass of the stars in that part of the galaxy are made of elements that are heavier than hydrogen and helium. Right? The more heavy elements there are, the older those stars likely are as well. And you can see that the oldest stars are not in the center, but kind of off to the side, these red things. That's cool, right? Each one of these little bits of information, and then you can go outward from the center, you can see how the stars, on average, get less metal rich or younger on the outside. But the exceptions are along these dots. The red parts, there's a ring of what appear to be older stars surrounding younger stars and then older, younger. It's great. This is a treasure trove of information for those of us who are studying galaxies. And imagine 10,000 of these, right? We're looking for them, and imagine if we could find all the E plus A, all these end of star formation galaxies, and see what their histories were in this multi-dimensional technique. So I've had students over the past 2.5 years, these are undergraduates mostly, look through Manga data as they've become available to look for E plus A galaxies. And well, out of now about 5,700 galaxies that have been observed, they have found 36. So they're not very common. Okay. But those 36, I am very excited about, because if we can study them in this kind of detail and interpret their histories, we are getting fundamentally new and original information about how galaxies age, what happens after their star formation ends. So, just by way of ending, this galaxy is a great cosmic laboratory. My favorite galaxy out there, although, you know, it's like they're all like your kids, right? They're all really cool. But this one is really neat because I've been following for a long, long time, and it's a great cosmic laboratory amongst the others, which I hope maybe you all will help me do, if you ever feel like it, to study the end of star formation in galaxies. So that's the end of my talk, and I'm happy to take any questions. Thank you so much. Yes, go ahead.
When you call a star old,
Yes.
what age are you putting on it? And the other question is, what is the star formation rate of our galaxy versus like our
Great question. Great question.
sister galaxy?
Good night. Thank you for coming. See ya. When I say old star, I mean like stars like the sun.
5 billion.
Okay, like 5 billion years old. That's legitimately old. All right. A 1 billion year old star is intermediate age. Right. Yeah, they're young, but truly young stars are things that are, say, less than 100 million years old.
But is our star, am I correct in saying that our star is, in terms of size, it's in the top 10%?
In terms of mass, it is kind of on the, it's more massive than most stars.
Does the age relate to size?
Age can relate to size.
Okay.
It doesn't always.
All right.
Stellar evolution causes stars to change size regardless of how old, depending on how old they are, and depending on how massive they were when they were first born, things like that. So it can be complicated. But normally, red stars are older than blue stars. That's generally the case. So when I say old, I mean like several billion years or older. These A stars are often considered intermediate age. And your other question was,
The star rate of our
stellar-
galaxy
yes.
versus Andromeda?
it is believed that the star formation rate of our galaxy and Andromeda is about 1 to 2 solar masses per year.
That's it.
That's it. And that averages out to about 10 stars.
But
Okay.
you called it an active galaxy.
But that's actually quite active. That's right. You know, if you're only forming a couple of solar masses worth of stars per year in a big galaxy that has hundreds of billions of stars, that's actually pretty active. It's amazing. Yeah. Remember how we galactic galaxy astronomers think, right? 100 million years is a blink of an eye. And in 100 million years, you form 200 million stars. That's pretty vigorous, right? And it's time average. Some years there may be none. Other years there may be a whole bunch, because star formation is normally not this sort of consistent, always the same, but it happens in packs and bunches. So yeah, a galaxy like G515 or Magellan forms 0 stars per year. Right? 1 to 2 solar masses worth is fairly active, and a starburst, something that's happening, like say the mice, the ones that are actually in the midst of collision, they can get up to 5 to 10, maybe 20 solar masses per year. So we're talking 10 times as much. There are some regions of starburst galaxies, and if you average them out to the size of the Milky Way, they would be hundreds of solar masses per year. But they're normally very compact. It's very rare that a galaxy as big as the Milky Way is lit up with star formation at those levels. It's a good question. Yeah.
So, is there a hypothesis floating around in this that I think you alluded to it, and you stated correctly, that when you have a collision, a major collision, not eating up little satellite galaxies,
Yeah.
you know, 2 hefty galaxies collide,
Yes.
that accelerates, you get starburst galaxies.
Yes.
Therefore, accelerating star formation, does that lead to what I'll call premature death?
Yes. That is it. That is precisely what we're talking about. I did allude to it, and I'm sorry I wasn't as explicit about it as that I could have been. But yes.
So similarly, if you had an isolated galaxy
Mhm.
that never ran into something similar in size,
Right.
you would expect its star formation period to be extended.
Right.
Right?
Right.
That's interesting.
Yeah. So you have this sort of idea that every galaxy has a certain reservoir of gas with which it can make stars. Left undisturbed, it will have some sort of steady state star formation process. In our case, the Milky Way, say 1 to 2 solar masses worth of gas turning into stars each year, and that can last for 1 billion, 10 billion, many billions of years. But if you take Andromeda and the Milky Way and smash them into one another, oh, that's going to happen, by the way, but it's 5 billion years from now, so obviously don't change your retirement plans. When they hit each other, their gas reservoirs are going to be combined and quite vigorous. So if at that point the combined star formation rate goes to 10 times what they used to be, then it will be used up in 1/10 the time. And then the star formation shuts off because you've run out of gas. You've run out of material. Another way you can shut off star formation is that if the energy of the collision translates into so much dynamic energy of the material inside that it drives gas out, that can also stop star formation. So we don't know exactly how often it is that you run out of fuel and how often it is that the fuel systems are disrupted. But that's a big question that's going on right now in the quenching arguments. People are looking.
So follow.
Sure.
So my understanding of how spiral galaxies form stars in the arms,
Yes.
so those are pressure waves moving through background density of gas. I might
Yes,
have this wrong.
it is generally correct. I believe that spiral density waves are causing the gentle turbulence or disturbances that are causing stars to form.
So is another quenching mechanism in a collision the disorganization?
Yes.
It would then stop these nice pressure waves from processing?
Yes. The disruption of these, as you call them, gentle activities or motions inside galaxies may well be disrupting star formation as it goes on. Oh, Dan, you're awesome. Thank you. And the problem with that hypothesis is the problem with that hypothesis is that when the galaxies collide, they start forming their own dynamic systems, right? And they could cause, for example, gas to swirl toward the center of the common center of mass. And so what you're doing is increasing star formation. And by the time that collisional stuff ends, about 1 billion or so years later, those gentle systems may build back up again. We don't know the answers to those questions because the star formation physics at the level of, say, individual stars and solar systems, compared with the solar system, not the solar system, but galactic physics of something like a spiral arm, they're so different in scale, right, that we still don't have a good understanding of how one translates to the other. And people who are doing numerical computations with supercomputers are trying to bridge that gap, but it's still a very, very big gap to bridge. So, great question. Someone had a question up here. Yes, over here. And then,
Just a small question on that hexagonal fiber optic thing. How long an exposure do you take to get those spectra?
about 3 hours.
Really?
Yeah. Some of the brighter objects, if you're looking at a big bright object, for example, this 127 fiber thing, you're usually looking at galaxies that are not that far away, a few 100 million light years at most. In that case, you can get the spectra in about an hour. Okay. But for some of these ones that are here, for example, they're much further away, and they might be 500 million or 1 billion light years away. 3 hours is necessary to get good signal to noise. And even then, these fibers are sometimes frustratingly low in their signal to noise, so we have to bin them together. They're mapped together to a sort of a spaxel map. Not pixel, but spaxels, because it's a spatial pixel, right? And then these have to be combined, these have to be dithered. It's a lot of games we have to play with the same galaxies.
Wow.
Yeah, it's quite something that I have to give tremendous credit to the observers of the program because they're exquisitely careful in what they do. It's really amazing. Yeah.
I'm just curious, what is like the distance of G515? Like, do you know like the magnitude or anything?
The redshift of G515 is 0.0875, which puts it at a geometric distance of approximately 1.2 billion light years away from Earth. That gives, yes, its absolute magnitude in the R band is about minus 23. So it is big. It's a significantly large galaxy. It's very consistent with two already decently large galaxies smashing together to form one really big one. So it's a honker.
I would have thought it was like maybe 500 billion.
Is that an okay word to use?
I'd use it if you had.
Okay.
It can't be any less scientific than Magellan.
Magellan the honker. Okay, that'll be interesting. Yes.
I'm just, I don't know much about this, but I'm just curious where this gas comes from. And we have reason to believe once the galaxies collide,
Yes.
there wouldn't be new gas.
Great question. Interstellar gas in galaxies, almost all of it is believed to have been formed within a very short time after the Big Bang. Okay, and it's just basically floating around, hydrogen and helium and tiny bits of other trace elements. And then over the course of hundreds of millions of years, there's that large-scale structure of the universe, the cosmic microwave background. They have dense and sparse areas in the universe. What happens is that the gas starts to collect along the slightly denser parts. And then the more they collect, the more gravity they have, the denser the gases as a result, the more gas falls into these pockets of density, and eventually enough gas comes together to form galaxies.
So you're
It
saying
starts
that
with galaxies.
there wouldn't be new gas if there's no another Big Bang?
That's a great question. In all likelihood, no. The amount of gas that we start at the beginning of the universe is probably about all there is. There are caveats to that, right? First of all, gas is still falling into galaxies, right? And clusters of galaxies. As the stars form, then gas forms around it, and then other stars form, and they form galaxies. Meanwhile, as galaxies form, other galaxies are forming near them. They form clusters of galaxies, and they have these superclusters, right? Filaments, all that large-scale structure, cosmic web stuff. So gas is always continuously falling in to these systems. We just don't know how much, and we don't know if it's enough to sustain any new star formation. How much is falling in at any given time? Right? That's actually an interesting study. A lot of people use radio telescopes and look at the H1 21 centimeter emission to try to figure out that stuff. Now, as for whether or not more hydrogen is ever formed in the universe, that's really hard to say. Right? We have a lot of energy floating around in the universe. So sometimes you can produce protons. You can imagine something like pair production that produces electrons. But those are rare events as far as the universe overall is concerned. In a large sense, if I remember correctly, what we started with is pretty much what we have. And it's a matter of all moving it around. And putting all the protons together, making neutrons, making molecules, and then breaking up the neutrons and protons, pulling them apart, all kinds of fun stuff. Yeah, it's neat. Question back here, and then we come back this way. Is that okay?
What
Back here too.
causes the galaxies to collide with each other? Like, why do they collide?
Probably they collide purely from random motions that were formed early in the structure formation of the universe. Those cosmic web pictures, the galaxies are moving randomly, and then they start being attracted to centers of gravity. And if the galaxy happens to be nearby and they're moving toward each other, then they wind up colliding. There's probably nothing more than that. Just gravity and the random chance motions and superpositions of the galaxies themselves. Yes, and then there's, right?
So that really
Oh,
was,
back there too.
that was my question.
Oh, okay.
I'm curious about what consideration is given to understanding how that whole process begins, how one galaxy will start attracting another. Is it the presence of a super black hole? Or is it just, as you said, just the trajectory that they're on and they get too close to it?
It appears to be the trajectories. There are many of my colleagues do these massive cosmological simulations. If you ever want to look one up, there's one called Illustris that has recently been done. It's fascinating. It takes a huge cube of space and just follows it from the Big Bang and the cosmic microwave background to the present day. You can watch the galaxies in sort of super speed time, colliding and collapsing. And it just seems to be just random initial conditions that have led over billions of years to gravitational interactions. Is there anything more deep than that? I don't think I can answer that question beyond that point. But yeah, it's kind of cool to be able to see that sort of stuff happen. Yeah, totally see some of these movies sometimes. Illustrious, the Millennium Simulation, which was done around the year 2000, also has really good stuff too. So feel free to take a look at that. Here and then there. Is that okay? Okay, go ahead.
Yeah, in reference to your discovery, you said the black hole that could be heating up the dust and come alive again.
Yes.
Does that help in understanding those who are studying the black holes, or those that are alive, not alive, and for each galaxy that has one? That it's, in other words, the black hole within our galaxy is kind of dormant necessarily.
Yes.
Right. And basically, they're there, but they're not active doing anything because there's nothing happening necessarily
Right.
at them at the same time.
Yes. The evolution of black hole populations in galaxies is one of great interest to a lot of people. If you want to think about one of the most important changes in our understanding of galaxies in the past, say, 25 years, it's one thing that, say, this Hubble Space Telescope has helped us understand, is that just about every large galaxy has a supermassive black hole at its center. So this kind of supermassive black hole, which is currently sputtering, but probably used to be very active, and may eventually wind up being dormant, like our Sagittarius A star in the Milky Way. All these black holes add to our understanding of how galaxies change over time. And you can imagine also, if you think of a black hole not just as creating radiation as a result of its gravitational activities, but just gravity, throwing stars around, right? Stars that would ordinarily just be orbiting in some way, but because they pass through near the black hole, start being thrown into these strange shapes and configurations. That's a very interesting question that a lot of people are working on. Yeah. So that's a good insight on your part. Both of you next to one another. You want to go first? Okay. You guys have so many questions. Thank you.
Like you said, that some galaxies that are dying out, right?
Yes.
And in those galaxies, you have supermassive black holes that are also dying out.
Yes.
In theory, what happens to the stuff that is being sucked in by the supermassive black holes while they're actually dying out or after they die out?
What happens to the black holes themselves?
No,
Or the material that falls in?
that is being,
Okay. Well, first of all, it's a great question. What happens to the material that goes in the black hole? But I want to caution you not to use the word suck when it comes to black holes. Okay? Because black holes don't suck. The gravity is often, I can't remember, it was Jim Peebles or... I know. The term suck is just a thing that I like to remind people not to use when it comes to gravity. Because although it's fun, right? I think it was Jim Peebles at Princeton, I can't remember who it was that told me this, that he used to say in his introductory astronomy class, the thing about it is that gravity really sucks. Right? Everybody laugh. But it's not sucking. It's the curvature of space-time caused by mass. So things fall into black holes. All right? And there's a very famous song that Harry Belafonte sang once about that. It's, black holes don't suck. But if you fall in one, then that's your new home. No, they don't suck, they don't suck, they don't suck, they don't suck, no they don't. But if you fall in one, then that's your new home. So remember, black holes don't suck. But the good question, what happens to stuff that falls into black holes? Well, Stephen Hawking spent the last part of his life trying to figure that out, theoretically, right? It looks like what happens is that when stuff falls in, it comes back out very, very slowly through a process we now call Hawking radiation. Essentially, the event horizon of the black hole is not a solid boundary, but rather it's a quantum boundary. And so every once in a while, material can come back out. When it comes back out, it does come out as particles like the ones that went in, but they've been completely jumbled.
you mean after it dies out, then it's coming out, or it comes in and then
It goes in, and slowly starts percolating back out. Okay? So a black hole,
Over trillions of years.
over
But slowly.
even many more than trillions, yes. A black hole the size of our sun, the mass of our sun, not even the size of our sun, but the mass of our sun, would take, see, I'll make sure you get the number of zeros right. A billion, 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 100 million years to evaporate through Hawking radiation. But it can be built in much shorter than that through stellar evolution. Right? So right now, remember, the universe is only 13 billion years old, plus or minus, well, it's almost 14 billion years old. But so those other extra billions, we have to wait a really, really long time for the black holes to evaporate. So all of those black holes are still sitting there, and the matter's there, and as it comes out, we eventually wind up with everything that was in there. Black holes are not, say, rips in the fabric of space-time that conduit to other space-times. Okay? Rather, we can think of them as giant cosmic hernias, where the matter bulbs up underneath in the different space-time thing and slowly comes back out.
So theoretically, actually, stuff can form inside. You know, if you have so much stuff coming in, you know, then you have those clusters of this matter, and actually can.
The laws of physics are simply unknown within the event horizon of a black hole. We could have 1,000 pink elephants dancing inside there going, yeah, 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 but we would never know. People have started thinking about this, but there's really no good way to know for sure what would happen inside. Some people years ago thought that maybe black holes had entire universes inside them, where they might have their own laws of physics, where they might have their own kinds of life or consciousness or whatever.
But like with this I-band, let's say, the stuff that you know you were directed towards the galaxy, but if you directed towards the black hole itself, I mean, what can you see?
Right now, not much. Regrettably, the black holes are black and holes. So we try to get, sorry, astronomers are not particularly creative when it comes to naming things, right? If it's red and it's a giant star, it's a red giant. If it's dark and it's matter. If it's a medium that's sort of in between the stars, it's the interstellar medium. Sorry.
If it's spiral shaped to the
If
galaxy.
it's spiral shaped, the galaxy, the spiral galaxy, that's right. So we don't really know what's inside. Every time we try to look inside one, nothing comes back out so we can see it. But it's the object of a great deal of speculation, right? One only needs to watch movies like Interstellar to think about that.
All right, thank you.
No problem. It's a good question. All right. By the way, Stacy's my colleague. We work together on various things, but it's nice to see her here this morning. Yeah.
Nice to see you here. So, obviously, this is way in the future. So, when Andromeda and the Milky Way collide,
Yes.
do we know enough about the trajectory to know exactly like where it's going to hit and what effect it would have on our solar system?
We do not yet know what effect it will have on our solar system. Some people have speculated based on our rotations and so forth. There is a guy named John Dubinsky who's based at the University of Toronto, and he's done some very interesting simulations, computer simulations of what would happen when the Milky Way and Andromeda collide. So
Bad things, I bet.
generally tough things. However, there are a couple things that we think we know. First of all, the stars, generally speaking, with the exception of some clusters, are so far apart that even as the galaxies collide, the stars themselves will not hit each other. They'll pass by each other. They may cause gravitational chaos, throwing planets away and changing the orbits of things. But they're not likely to actually smack into one another because they're so far apart. It's like a swarm of bees coming through and they all somehow miss each other. So that's one thing that we know. Now, the other thing we know is right around that time, our sun is also going to turn into a red giant. Right? It will consume Mercury, it will consume Venus, it will burn off, turn Earth into a cinder and Mars, it'll blow off Saturn and Jupiter's atmosphere. So, if we're not, that's the sound. Yeah, that's what will happen.
You gotta get notified on your cell phone.
That's right. Good.
only 3 billion years away.
Yeah. So if we're still on Earth at that time and our survival is linked to the existence of our planet at that point, we're doomed anyway.
More than any of the
Yeah.
solar systems.
So I would like to think, yes, that we're not tied to our solar system by then. Keeping in mind also that 5 billion years from now, whatever we humans might be then, hopefully will be more advanced, right, evolutionarily than us, as we are from like the amoebas, which ruled the world a billion, years ago, something like that. So that would be nice, One of the great short stories of science fiction, in my opinion, of all time, was written by Isaac Asimov. It was called The Last Question. Those of you can still find it online. The Last Question by Isaac Asimov. I am told that he liked that short story most as well, of all the short stories that he wrote. It's what basically happens to humanity as time goes on and on and on. It's kind of an optimistic view of the future of humans, right? But also it's just kind of a neat idea that, yeah, by then we really aren't going to be tied to our solar system. So I think we'll be okay.
The last one.
The last question.
Question.
Last question. Not to be confused with the answer, which is also another. It's another
42.
story. That's right, 42.
Let's do.
Okay.
Yeah, all right.
Hey guys, it's continued to rain, so there's quite a bit of flooding out. So